Kampa, ga, lombo, gala, ga, qua. Okay? I always wanted to make a speech in Klingon. So in case any of you missed it, what that was, it was, I wish you an honorable afternoon, you weaklings of the Federation. Before we get stuck into this, I wanted to get a sense for the kind of Trekkies that I got here today. So let's sort of go around the room with a show of hands in terms of who is your favorite captain. Okay, so who is for Captain Kirk? Captain Picard? Yeah. Captain Janeway? Commander Sisko? Ooh, 2. Captain Archer? Captain Lorca? Well, okay, so it's Captain Picard versus Kirk, really, yeah. So it's really sort of a bastion of the old guard here. Very, very good. The classic. I wanted to start with this. Oops. An homage to Stephen Hawking, of course, recently passed away. And this is a scene from an episode in season 6 of The Next Generation, when Commander Data plays poker with Einstein, Newton, and Hawking. And of course, Hawking is there playing himself. The first time ever somebody showed up in Star Trek and played themselves. And he's playing poker with the 3 of them because he wanted to understand in the episode how the 3 greatest minds in physics would interact with each other in a situation like this, a poker situation. Unfortunately, Hawking complained at the end that because the poker game was interrupted by a red alert, he never got to collect his winnings at the end. So he had to leave before he could get his 140 Federation coins. But nobody could tell him what the exchange rate was, so he wasn't too unhappy about it. So we're here today to discuss whether anything like this can actually happen in the near or far future. I'm a physicist in the astrophysics group here at Imperial. And what I'm interested in my scientific research is the big fundamental questions about the nature of the universe, dark matter, dark energy, the Big Bang. But of course, Star Trek shows us a universe where many of the impossibilities of physics are torn to shreds, actually, in order to give us interstellar travel, exciting new voyages, and the continuing mission of the Starship Enterprise. And the question we want to ask today is, how far away are we from seeing the reality depicted in the various Star Trek series and movies? And can we ever get there? What does physics tell us about the feasibility of the voyages of the Starship Enterprise? Of course, many of the technology aspects that we've seen across the years have come to pass much more quickly, perhaps, than even the show creators imagined when they put them in. Here, we're seeing gigantic touch screens on the wall, and here the console in the engineering room of the USS Enterprise D. Of course, touch screens are an everyday occurrence now, not even 30 years after this was shot. If we go back to the original series, Commander Uhura here, Lieutenant Uhura, is seen with a futuristic looking in the 60s iPad, and nobody flinches an eye at an iPad nowadays. Captain Kirk himself with a communicator. We have communicators in our own pockets nowadays that are many, many times more powerful than anything we saw on the series 50 years ago. And so in many ways, the pace of technology has been much, much faster than even science fiction writer could imagine 50, 30, 20 years ago. And so we really walk around with technology that was science fiction 20 years ago. Imagine that. So as Yogi Berra used to say, predicting what the future might bring is always tricky, especially about, making predictions is always tricky, especially about the future. But the one thing that really sets the universe of Star Trek apart is this, the fact that they've left Earth, exactly Earth, our planet, they left it behind. And so really it's a space opera. And so we need to look at what's out there and can we ever get there, just like the Starship Enterprise did so many times. So perhaps the most striking feature of the Star Trek universe is the fact that it's populated by many characters, not just humans, but things, species like Ferengi, for example, and all of them come from different parts of the galaxy. So really, we're seeing a universe that's teeming with life and life forms, all of whom conveniently speak English and are not too dissimilar to ourselves, but still. So the first question I guess I want to ask today is, what do we know about life elsewhere in the universe? And are we ever going to meet the Ferengi? The first place to start our exploration of the universe is our backyard. So here is the solar system. We are here, the third planet in Earth, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, all the way to Pluto out here. And over the years, we've explored the planets of the solar system using robotic means of various kinds. And we now know that we are just one of the many, many systems that really fill the galaxy with potential places for civilizations to flourish. We are here, that's an outside view of our Milky Way, reconstructed. We are here just one of about 300 billion stars in the Milky Way. But what we have learned over the years is that none of those planets harbors life except Earth. And so if you go even to our nearest neighbor, Mars, you see a planet that is in many ways similar to Earth, but it's a little bit further away from the sun, meaning it gets less light, less power, and certainly no life, because water, if there was water on Mars, has evaporated over the years. There's no longer liquid water on Mars, and the landscape seen by the rovers Discovery and Opportunity is desolate and empty. There is no life there, no civilized life, and not even microbes insofar as we can tell. And we've explored the rest of the solar system, and we know the conditions are simply not there for life to exist as we know it elsewhere. There are some places, like the moons of Jupiter, where we think perhaps deep down in the oceans, the conditions might be ripe for some sort of primitive life to exist, but nothing like the Ferengi, not the Klingons, and not the Vulcans. So where else should we look? The challenge is that anywhere else you look in space, well, there's a lot of it. And I just want to give you a sense for the scale of the challenge that we're facing whenever we want to start those voyages and get somewhere else to discover what's out there. Oops. Oh, that's interesting. Let me fix that. Yeah. Great. So here is a map of the universe showing one of the two coordinates on the sky. So that's essentially where things are around us, just one angle in the sky. But that's not the one that I'm interested in. I want you to look at this scale here, because that's distance from us. So where one unit is one Earth radius. So that's 1,000 Earth radii away. That's 1,000,000 Earth radii away. You can see things that you're familiar with. Here is the moon. Here's the sun, Mercury, Venus. This band here is the asteroid belt between Mars and Jupiter. Jupiter, Saturn, all the planets of the solar system up here. That's as far away as we've gotten. That's the Voyager 1 and 2 probes, which were launched in 1977, 1978. And only now, after 40 years of space travel, are they getting at the edge of the solar system. Okay, so we've not even left the edge of the solar system, and those probes travel at about 17 kilometers per second. That's pretty fast, and yet they're not even out of our own solar system. And if we want to go and find life elsewhere in the universe, well, we need to leave our solar system and go and find other planets around other stars. Problem is, between us and the nearest stars here, there is a great deal of nothingness. So here, we got millions and billions of kilometers to cross before we even hit the nearest star, Proxima Centauri, which is 4.2 light years away, meaning light takes 4.2 years to get from Proxima to us. Problem is, with conventional space means, you would get there in, give or take, 27,000 years. Not very practical, especially if you want to shoot a successful TV series. There's a lot of waiting around all the time. So really, no. And then beyond that, this blob of points here is the Milky Way. The new Gaia data that have hit the news the other day have just been released. 1.3 billion stars have been mapped by this spacecraft called Gaia. This is a previous version of that data set. All I want you to take away is that there is a lot of them. And look at the red dots. Those red dots scattered around this cloud, those are planets orbiting other stars in the Milky Way. So if we only could get there, chances are some of them will harbor life. We'll go through the maths in a minute. Let's not even talk about what's out there Each one of those green dots is an entire galaxy. There are about 50 billion galaxies in the visible universe, each one of them with about 300 billion stars. If we take a conservative estimate of how many such stars have planetary systems around them, we come to the conclusion that in the visible universe there are about 2,000 billion planets. So chances are life is somewhere else out there. Question is, can we ever get there? Because the big discovery of our times is that there is plenty of planets. About 1 in 2 stars contains a planetary system. Here is a compilation of about 3,000 planetary systems that have been discovered going around other stars. And you can see there are big planets like this one. There are small planets. There are big orbits, small orbits. It's an entire zoo of possibilities. Some planets are like Earth, we hope. We hope to find some that look like us. Some are completely different but could harbor a different type of life, precisely because life could thrive under very different conditions. After all, we've seen life emerge in the universe precisely once here on Earth. We have no clue what other possibilities are out there. And in fact, the one thing that we know for sure is that the things that we see on Star Trek are too conservative. They look too much like us. Life elsewhere in the universe likely will look very, very different because it will have evolved under very different conditions than here. We also know that there are planetary systems that orbit binary stars. That's to say, planetary systems that have 2 suns, which is something that we've seen elsewhere, of course, in science fiction. Perhaps a visionary view. So it's not enough to find planets, because there's plenty of them, but most of the ones that we've found so far are either too big, too cold, too hot, typically, to have liquid water, and we think water is really, really important for life. So the quest really is not just to find planets. Each one of those dots is one of about 4,000 planets discovered, or at least potentially discovered by the Kepler mission. The point is that can we find one that's just right for life? And so we're looking for a planet that's not too big. It's not like Jupiter. It's not like Neptune, but it's the size of the Earth. And we're looking for a planet that doesn't go around its star in 1 day or 1,000 days. It goes around its star in about a year. Because if the speed is not important, it's the distance that's important. Because if you go around so fast, it means they are very close to the star. You're going to fry on those planets. If they go around much more slowly, they're very, very far away. You're going to freeze. So you really want a planet that's around about this point here. You can see we found lots of them, but around here, not so many. That's not necessarily because they don't exist, simply because we don't have the observational capabilities yet to see them. They're difficult to spot. But if we zoom in the region here where we think life can exist, then things become a little bit more interesting. So in reality, the important thing is that the energy that you receive from your star is not too much, otherwise there wouldn't be no liquid water. It's not too little, because otherwise, if there is water, it would freeze. It's got to be in this Goldilocks green zone. So that's how much energy you receive, and that's the temperature of the star. And so we are here, and these other dots all around are potential planets that we have found, and that we think could have potentially, based on these characteristics, the opportunity to harbor life. So really, if you do the math, things are in our favor. In our galaxy alone, even if we look only at habitable planets, we think there is a potential for about 5 billion of them. So really, the probability is on our side. Ferengis might not be out there, but something like them probably is. So we're probably not alone in the universe. The question is, even if we were able to spot them at distance, can we ever get there? Because I mentioned before that space is incredibly, unimaginably vast. So to cross those distances, conventionally chemically powered rockets simply won't do. We need something else. In the pilot episode of Star Trek: The Next Generation, the Enterprise travels to Farpoint then they get intercepted by Q, and so they get diverted, and so on and so forth. So Farpoint station orbits a star called Deneb. And Deneb is about 2,700 light years away from us. Getting there with conventional propulsion would take millions of years. We need something else. And of course, Gene Roddenberry knew what was needed. Cool stuff, huh? I love it. But does physics allow it? Can we even dream of ever being able to put something like this together? Because warp propulsion really is what's needed for us to overcome the speed of light barrier. And the speed of light barrier says that nothing can travel faster than 300,000 kilometers per second. And you think this is pretty fast, but space is so big that 300,000 kilometers per second is really is a snail's pace. So first of all, faster than light propulsion then, warp speed. Is it possible? Well, conventional wisdom and physics 101 say no, because light is the barrier and nothing can travel faster than light. Actually, there's a catch. That's the interesting part, because in fact, faster than light speed, if not exactly travel, and I'll tell you the difference in a minute, is actually very, 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 very possible, which is something that contradicts what you've heard perhaps before. In order to understand that, we need to take a step back. And the step back is to think about how our universe actually changes with time. Because Hubble, in 1929, discovered that the universe is expanding, that the galaxies that we saw before in that map are not static, but they're actually being blown apart from each other by the expansion of the universe itself, which began 13.7 billion years in the Big Bang, with the Big Bang. So I got here a model of the universe that I made in my kitchen the other day. It's a focaccia, though. No, really. I filled it with olives representing galaxies. So our Milky Way is this, the black olive in the center. The other olives are other galaxies. And as time goes by, the focaccia dough rises, just like the universe expands in time. As you can see, the galaxies move away from each other. They move away from us, which is what Hubble discovered, but crucially, they also all move away from each other. The universe is expanding, which means that every galaxy is moving away from every other galaxy. And therefore, the universe becomes bigger, and all galaxies are stretched away from us by the expansion of space-time itself, which in this analogy is a focaccia dough. Once you're finished with the experiment, you put it for 200 degrees for 50 minutes in the oven, and then you eat it with friends, which is also very, very nice. And so the point is that galaxies are moving away from us, and this picture here, taken by the Hubble Space Telescope, shows a field that would fit inside the eye of a needle held at arm's length. So it's the eye of a needle on the sky, but looked at very, very, very carefully. And there are 5,500 galaxies inside that eye of a needle. Each one of the dots on this image is not a star. It's a galaxy, and each one of them contains about 300 billion stars, and then the planets going around them, et cetera, et cetera. But the point I want to make is this. All of those galaxies are moving away from us, and most of those galaxies are moving away from us faster than the speed of light and always have been. And that is because space-time is expanding between us and those galaxies, and it's dragging them away faster than the speed of light, which is perfectly feasible even within, actually, it's predicted by Einstein's general relativity, and it breaks the speed of light barrier for the reason that those galaxies are not moving anywhere in space-time. It's space-time itself that's stretching faster than the speed of light. That's perfectly allowed. There is no barrier to that. And actually, those galaxies prove it, because we can prove that those galaxies are moving away faster than the speed of light. And yet we can see them, which is a paradox that I don't have time to go into, but believe me. So the fact is, we can, in principle, it's possible. In other words, if we go down this path, then our warp drive is not about moving the spaceship through space-time faster than the speed of light. That wouldn't work. But if we can move space-time around the spaceship, which is kind of what the warp drive is supposed to be doing, actually, yeah, it's just about possible. A Mexican physicist called Miguel Alcubierre, actually put some numbers together and came up with a configuration of the Einstein's field equations that allowed that to happen. So in principle, it is possible to move a particle across space-time by making space-time slide under the particle. There's a catch, though. He made the calculations for a single electron, which is probably smaller than the Enterprise. And he found that the energy needed to do that is a kind of energy that we have plenty of in the universe. It's called dark energy. It's an energy with a property that makes it have negative pressure, very special type of energy. We've got plenty of it in the universe, thankfully, Problem is, move an electron faster than the speed of light, you need the equivalent amount of dark energy contained in about 50 times the size of the visible universe. So that's an engineering problem. You know, I'm a physicist. I'll leave it to Scotty to sort out, right? I mean, he knows how the things go. Fortunately, though, okay, maybe warp drive's not going to happen. But hey, you've got other ideas in Star Trek. What about the Spore drive? Yeah? That's quite cool. That's even better because it gives you instantaneous dislocation. You don't even have to wait around. And you can do all sorts of tricks, play all sorts of tricks to the Klingon in the meantime, which is very, very good. Now, of course, instantaneous dislocation, simply, it's a no-go, right? That doesn't exist. You can't do that. It breaks all the known laws of physics and some more. But the one thing I want to bring up is this. Oh, let me take the lights down. I'm flicking between the lights back and forth because I don't want you to fall asleep, right? So the Spore drive is supposed to work by riding on the mycelial network, right? So, you know, what about the mycelial network itself? Well, we don't have a mycelial network out there, we don't think, but we have something that is kind of looks like the same. So what is this here is a simulation on a supercomputer of what the dark universe will look like. That's to say, what the dark matter universe looks like if we were able to see dark matter. Now, we can't see dark matter. And actually, dark matter, we think, is a new type of particle which is streaming through us as a shower, like a shower, even now, here. If you put out your hand, or even if you don't, there's about 12 million particles of dark matter flying through it every second, yet we don't feel it. And you can see in this simulation that actually we think that the entire universe is filled with this dark matter that we cannot see, and the structures that this dark matter forms, brought about by gravity, which are these filaments here, are pretty similar in a sense to the mycelial network that Discovery came up with to get them to travel faster than light, etc. So while we certainly cannot ride these filaments, it was interesting to me when I saw Discovery that they came up with an idea that in many ways is similar, at least in appearance, and this idea of a network spanning galaxies and crisscrossing the universe, very similar to what is the cutting edge state of knowledge in terms of what is the fundamental scaffolding of our universe today. So the Spore drive won't work. What about this, the Bajoran black hole or wormhole of Deep Space Nine? Exactly. So that's another convenient shortcut, to get you to the delta quadrant in no time. Hey, why not? So we certainly have knowledge of black holes. That's something that we've seen, we understand. Hawking himself did great advances in terms of the physics of black holes. And what are black holes? Well, black holes essentially are a very, very, very strong concentration of mass, a concentration of mass that will effectively bend the space of the shape of space-time to the point that space-time will get a puncture. Right. So the way to understand that perhaps is put in the simplest possible words, I hope, in a little book that I happen to have written. So I'll just read a very brief sort of general relativity 101 excerpt from the book, because the book is a book about the universe, cosmology, everything that we've talked about, except all real. But written using only the most common 1,000 words in English, and the universe is not one of them. So it was a little experiment to see whether I could take complicated ideas like black holes and transform them into simple words. So let me give you a little introduction to general relativity using only the most common 1,000 words in English, where general and relativity are not on the list, of course. So Mr. Einstein said that space and time had to be married and form a new thing that he called space-time. Thanks to space-time, he found that time slows down if you fly almost as fast as light, and that your arm appears shorter in the direction that you're going. He then asked himself what would happen if you were to put some heavy stuff, as heavy as a star, in the middle of space-time. He was the first to understand that matter pulls in space-time and changes the way it looks. In turn, the form of space-time is what moves matter one way or another. As an idea, this was very different from what Mr. Newton had said a long time ago. For Mr. Newton, space and time did not talk to each other, never married, and lived different lives. So the great insight of Einstein was that space and times are not a fixed, immovable entity, but they're actually bendable and flexible, just like a rubber sheet. And so if you put enough mass, condensed enough sufficiently, 1.4 times the mass of the sun, you're going to you're going to change the shape of space-time so much that you're going to rupture it, create a singularity, and that's a black hole. So a black hole is fine, but of course if you want to be able to pop up on the other side, rather than being just spaghettified and die a terrible death, you need something else. You need something that looks like this. You need a wormhole. So you take one black hole here, you take another black hole there from somewhere else in space-time, far away preferably, and you join them up nicely, like so, so that you have a traversable wormhole, and boom, you are on the delta quadrant. So some colleagues of mine, Luke Butcher, actually did some heavy calculations to figure out something that would not be amiss, in Data's mouth. That's from a real scientific paper in 2014. We calculate the Casimir energy momentum tensor induced in a scalar field by macroscopic, ultrastatic, spherically symmetric, long-throated, traversable wormhole, and examine whether this exotic matter is sufficient to stabilize the wormhole itself. Mr. Data, come to the point. We find that the throat closes slowly enough that its central region can be safely traversed by a pulse of light. So maybe not the Enterprise, but a pulse of light perhaps. So there are solutions to Einstein's equation that allow a traversable wormhole. That's not to say that they exist in nature. That's certainly not to say that we can manufacture one, but there are solutions that allow at least light beams to go through. So again, there is hope after all. And we've seen very recently that this fantastic theory of relativity that tells you that the shape of space-time is bendable, etc., has been proven right yet again by the spectacular discovery of gravitational waves in 2016, which was awarded the Nobel Prize for Physics last year. So really, the fact that space and time are bendable and flexible and even sustain these gravitational waves that are ripples in the fabric itself of space-time has been proven correct. And so yet again, it might be that Einstein's idea have some twist in them that will allow us one day to at least understand, if not create, traversable wormholes. And so my final topic is one that I think no survey of the Star Trek universe would be complete without. The transporter, right? The transporter is fundamental in the Star Trek universe, not least because Gene Roddenberry devised it as a way of getting people from the starship to the planet without having to spend money on special effects all the time, and putting them on shuttles and all the rest. So the transporter, done. They're just on the surface in no time. So the transporter is this idea that you can dematerialize somebody, transform them in some sort of wave energy, and then beam them across and reconvert them into matter. So what's the physics behind? So in order to understand whether this is even possible or conceivable, we need to think for a little bit about the crazy world of quantum mechanics. Now, quantum mechanics is this crazy theory. I mean, one of the founding fathers of quantum mechanics famously said that if you think you understand quantum mechanics, then you don't. Rightly. We still teach it as if it made sense, but it doesn't. And one of the things that doesn't make sense is that particles in quantum mechanics can be both waves and particles at the same time, or actually depending on circumstances. So here's an experiment of quantum weirdness. So say that you have a light source. And light, as everybody knows, is made of waves. And so if you take these waves, those are crests of waves of light coming through, you make them pass through two slits, a little bit further apart from each other, then you generate a new wave at each one of the slits, and the waves, just like waves in a pond, as they pass through the slit, they will interfere with each other, meaning that the crests will cancel out the troughs, just like waves on a pond would do if you throw two stones in it. And so at the end, what you get here is this characteristic pattern of light that we call an interference pattern. So there are places where you get light and places where you don't, because the white places is where the crests and troughs cancel out. We call this phenomenon interference. So that's all very well, but then let's make a slightly different experiment, because as we all know, light is also a particle. We talk about photons, and Einstein actually said that the energy that photons can carry is quantized, so there's only discrete packets of energy that can be carried by photons. And so if it's a particle then and not a wave, it's impossible for it to go through both slits. It has to go through either one of the slits, right? If it's a particle, it has to go either here or there, but it can't go through both at the same time. So we can actually put a camera here to detect whether or not the photon passes through this point or that point. And here is the miracle. When you change the experiment, it's the same experiment, it's the same source of light, but when you put a camera in, which tells you which way the photon went, the interference pattern disappears, and you get only 2 spots of light. It is as if light knew what you are up to as an observer and changes its nature accordingly. Well, nobody's looking, I'm going to be a wave. Oh, you put a camera in, I'm a particle now. Right? That's crazy. And yet it's not just an idea, it's experimentally proven. Everybody's heard about the famous cat, yeah? Again, the idea that the cat can be both alive and dead at the same time, and yet until you look, it's not the question that the cat is either dead or alive. The experiment is that the cat is alive and dead at the same time. And in fact, people have made this experiment shooting not particles of light, but electrons. Electrons which we think of as particles. But actually, the flip side of what I just told you is that a particle can also behave as a wave. And so the idea was this, to trick nature, to trick quantum mechanics, and say, all right, electron, you're a particle. What about me shooting 1 electron at a time through the slits? And I shoot 1 electron at a time, so the next electron doesn't know anything about the previous one, and the previous one doesn't know what the next is going to do. You can't talk to each other across time. Let's see what happens. And this is what happens. So prepare to get some frisson down your spine, because that's as spooky as it gets. So you shoot 1 electron at a time, and you can see they kind of form a random pattern at first. Clearly, electrons, they just travel. They mind their own business. But if you shoot enough of them, and enough of them, and enough of them, look what happens. Interference. Right? Crazy. So electrons clearly know something about each other, even though this has been done over a period of hours. So that's all very well, because actually some other aspect of quantum mechanics we can use to transport things around. And so the idea of quantum teleportation is exactly to use this kind of quantum spookiness to take 2 particles and quantum entangle them. At this point, it comes a point of the talk where I just wave my hands around, okay? You understand why. Quantum entangle them so that they share, in some sense, a quantum state. Then you send one on this side and the other one on the other side of the universe. And then this particle here, the moment you measure the property of this particle, up until this point, the properties of the particle are unknown or in a state of superposition, just like the cat was dead and alive. The moment somebody measures the particle here, the particle over there, be it halfway across the universe, doesn't matter, instantaneously acquires the same properties. So this is, again, a phenomenon that's been proven experimentally. It's more a phenomenon of quantum communication rather than teleportation, because we're not really beaming this particle here over there, but what we're doing, we're creating a copy of this particle halfway through the universe. And this has been done, with light. The maximum distance that has been covered by this is about 1,000 kilometers. It's been even done with atoms, or at least one atom, and the maximum distance is a bit less helpful, 21 meters. But still. There's a snag. Okay, that's first of all quantum copying. It's not really quantum teleportation. So there will be still 2 copies of you, and you need to scale this up. Each ounce of material contains 10 to the 26 particles. And in the quantum teleportation experiments so far, the probability of success is 0.1%. So no wonder that Bones was so fiddly about it, and he didn't really like being teletransported around. So on this, I think, I'll bring this to a close. I'll leave you with the cosmic thoughts of how, physics can perhaps progress in the future, and how Star Trek has led the way in many ways, and might still lead the ways in some astonishing developments in physics. Like Scotty used to say, I'm only an engineer, Captain, I cannot change the law of physics. So, but who knows, maybe the laws of physics are in some sense more Star Trek-like than we ever knew. Live long and prosper. Thank you. Thanks. And I believe we have a few minutes for questions, maybe 5 minutes. I'm looking around. Yes, sir.
On how fast you can travel, I've heard that people are looking at an ion drive, which can take us faster than a chemical reaction drive.
Yeah, ion drive, yes. The question is how fast can we travel still by not breaking the speed of light? Yeah, I mean, there are some ideas. The ion drive, there's another one that I've researched recently about using nuclear-propelled engines. So essentially having a battery of atomic bombs going off behind you, which is I'm a little bit, I wouldn't be a little worried. So you can, with the atomic engine, you can get about a speed of about 1,000 kilometers per second. So that's kind of fast. It would take about 6 months to go to Alpha Centauri with this kind of speed. 6 months, yeah, to Alpha Centauri. Yeah, oh, yeah, okay, that's doable, but you have to be happy to sit on a series of atomic bombs going off below your, under your bottom. I don't know. You go first, okay? Yeah. That's right. So the question is, can we ever use this black hole, this wormhole, or are we going to be trapped inside? So in a conventional black hole, yes, you would be trapped inside, and even before you get trapped inside, you'll be spaghettified to death by the differential in gravity from your feet to your head. So not very pleasant. The whole idea of the wormhole is that you do not get trapped inside, but instead you get to traverse it and pop out on the other side, which is this trough that you saw in the diagram. Whether that's feasible or even possible in nature, or even whether they exist, is unknown. Yes?
Do you think that interstellar travel is possible in our lifetime?
Do I think that interstellar travel is possible in our lifetimes? Probably not. No. We might see people going to Mars, although, let me take a step back in terms of space travel. People say, oh, we've been to the moon. What's the big deal to go to Mars? Well, it's an order of magnitude harder. So Mars is 80 million miles away. Okay, the moon is 300,000 kilometers. It's nothing. It's not comparable. Whenever I hear Elon Musk and all the visionaries talk, it's all very well and good, but it's bloody tough out there. And we're very fragile beings, and to survive this voyage, even to Mars, is a big challenge. I'm not convinced that it's as easy as people make it sound. Interstellar travel, no way. Simply because of the scale, the magnitude of the gap that you need to cross. And plus, there might be nothing to go to, nearby. Proxima Centauri might have a planet, but it might not be habitable. And once you get there isn't even Starbucks. So, I wouldn't go. Yeah.
You mentioned that you thought that only half of stars had any planets. Is there a theoretical reason why half of them might not have any planets, or is that only experimental?
No. So the question is there a theoretical reason why 50% of stars have planets and others don't? No. Actually, it was quite a big surprise. When we started having the technology to see those planets, they started popping out all over the place, which is not what people expected. So in fact, the popularity of planets is a bit observational fact. But because the fact is that until 20 years ago, we only had one single solar planetary system to study, our own. So we thought, everything, if there are other planets, everything needs to be like this. All the planets that we found are completely different from ours, partly because of the way we discovered them. But there's a variety of shapes and size, and big Jupiters and small Jupiters, and mini Neptune and super Earth, which we had never dreamt of. So planetary astrophysicists are busy trying to come up with ideas how the things can form. We don't understand it yet. It's the data that are driving those. One final question, and then we'll shut this down. At the back, yes. Yeah. Yes, the young boy, yeah. Yes. Say again? What happens if you go with the speed of light in the black hole? Okay, so that's a great question. So essentially, if you're falling into a black hole at the speed of light, you will, because of the different rate at which time flows for you than for everybody else, as you look around you, time will appear to slow down. So you look around you, and so for you, time slows down, which means that everything around you in the universe will start going very, very fast. So you will see stars die, galaxies die, black holes form, all of it, while for you it's going to be like 2 seconds, because the time differential becomes extreme. So it's quite an extreme experience, and even simulating it is quite interesting, because you can really see how time is not what we think it is. It's something that flows differently at different places in the universe. So it would be a great experience, but then, when you come back, if you come back, there's nobody there to tell the story because they're all died. Sorry, I appear to be very bleak today. I'll let you go. Thank you very much for coming. It's been a real pleasure. Thank you.